we have just finished looking at graphing trigonometric functions. Now we're going to jump into looking at our inverse trigonometric functions. And so our objectives here are to define our inverse sine function, cosine function, and tangent function. Find a value of an inverse sine function, cosine function, and tangent function. Use properties of inverse functions to find the exact values of certain composite functions, and then define inverse functions of trigonometric functions. And lastly, to solve equations involving inverse trigonometric functions. So I wanted to review a little bit on inverse functions and properties of inverse functions, and that will help us go to graph our trigonometric functions and then to solve our inverse trigonometric functions at certain values. Okay, so just recall a couple of things about inverse functions. So a function f of x, if it's a one-to-one function, then the inverse exists. So our function has to be one-to-one in order for our inverse to exist. So recall that a one-to-one function that had to pass both the vertical and the horizontal line test. So function, for every value we plug in for x, we get exactly one value for y. But to be one-to-one, every y value is only given by one value of x. So the other thing to know is that if you take the composition between a function f of x and its inverse function f inverse of x, this is equal to x. So recall, you could write this a little bit, like with a little circle in between the f and the f inverse of x. This is equal to x. And it doesn't matter for a function and its inverse function, the order of the composition, you will still get back x. Normally, when you take a composition of two functions, order matters, and you would get back different things. And recall that composition is basically you're taking the one function. So like in this case, we're taking the inverse function and we're plugging it in wherever we see an x in f of x function. That's just another way to write it. So another thing to remember is how you found your inverse function. So if a function was one-to-one, and then it would have an inverse. And to find that inverse function, first thing you would do is you would rewrite f of x as y. Then recall you swapped your x and your y values. Once you plugged in y wherever you saw an x and x where you saw a y, then you're going to solve for your y value. And then once you get y by itself, you rewrite y as your inverse function, f inverse of x. So notice, if you're swapping your x values, which are our values in our domain, and your y values, which are the values in our range, to get the inverse function, our domain and our range for our function and our inverse function swap. So the domain of f of x, this is the same thing as the range in our inverse function, f inverse of x. Or if we knew the range in our inverse function, we could get the domain in our original function. And our range in our function f of x gives us our domain in our inverse function, f inverse of x. Okay, so those are just some things that would be helpful if you remembered how to do, or just remembered about functions and their inverse function. Well, the first thing that we talked about was that our function had to be one-to-one. And if you recall, so let's look at our sine function. If we were to graph f of x equals sine of x, recall this one started at our midway line. There's no vertical shift, so that's starting at our origin. And then at pi halves, we reached our max of 1. At pi, we came back down. hit the midway line, 3 pi halves, we got -1. At 2 pi, we're back up to the x-axis. And this repeats itself. This was just one period. Now I'm extending it on the other side of the x-axis. So if I did my horizontal line test, notice that I could draw a horizontal line, and here's one spot where this is intersecting more than once. So it doesn't pass that 1-to-1. It's not 1-to-1. So I don't know if you remember, but before in algebra, we could make our functions 1-to-1 by limiting our domain. So this is what they do. They limit our domain, and it doesn't matter where you do it, but to keep things nice, we're going to limit our domain between negative pi halves and pi halves. And so if I limit my domain between negative pi halves and pi halves, I've now made this function a 1-to-1 function. So we're going to limit the domain. Of f of x equals sine of x from negative pi halves. So that's less than or equal to x, which is less than or equal to pi halves. Or another way to write that, interval notation, so bracket, because we're including that value, negative pi halves, comma to pi halves. And we're including that value, so another bracket. So this, our domain of our function f of x, this is going to be the range of our inverse function. And so also let's look at this picture here of our sine function that we limited our domain, and let's look at the range. So notice that our range, the y values that we're hitting -1 at negative pi halves. We're hitting all the values between -1 and 1. And so our range of f of x is equal to -1 to 1. Or another way to write this is -1 is less than or equal to, this is our y value, which is less than or equal to 1. Okay, so let's now look at what would the graph of sine inverse of x look like. So looking at the graph of f inverse of x, we are going to swap our x and our y value. And so let's just rewrite this. And so now, because we're graphing the inverse function, and we would write the inverse function f inverse of x. So it kind of looks like a -1 exponent, but make sure that you don't think of it that way. That's just the notation for the inverse function. So f inverse of x, this is equal to sine. You're going to put what looks like the -1 exponent, but represents the inverse function before the x value. And they just tend to do that, like when we did sine squared of x, we put that square where that inverse function notation is. And it's just so that we don't think of the argument having that exponent. You might also see, if you watch other videos, or it might even be in our book, but another way to say sine inverse of x is arc sine of x. That's just another way of saying the sine inverse function. Okay, so we know that our domain of this function is equal to the range of our f of x function. So our domain of f inverse of x is -1 to 1, but this is our domain, so it's representing our x values. So we want to put -1 to 1 in here. And our range of f inverse of x, this is going to be the domain of our original function. And so that is -π12 to π12. So let's put those values on our y-axis. So we have -π12 and we have π12. So let's graph this. So here we had a point at -π12, -1. Well, that's going to be flop our x and y value. So our point on the inverse function is going to be -1, -π12. The point 0, 0 on the inverse function, well, swapping 0 and 0 still gives us 0 and 0. And then at π12 we had 1. So at 1 we have π12. Which looks like this. They almost look identical, and it just has to do with my my spacing, but it's pretty much the same kind of picture. Okay, so we're going to look at an example. We're going to try to find the exact value of our inverse functions. And so the thing that you need to be aware of is when we're dealing with these inverse functions, so the function or the expression it gives us, it starts with the inverse function, then we need to be aware of our domain and range. And so here for sine of x, we're always going to be between -π12 and π12. So we're kind of thinking backwards. And so it's really helpful that you knew your trigonometric functions at your special angles and at those reference angles. And if you don't know those, then you need to learn them, or this is going to be really hard. And you should be able to do this without a calculator. So here we're looking at sine inverse of √3/2. So we're trying to think backwards. We're thinking to ourselves, sine of what value is equal to √3/2? And that value that we're looking for, it has to be between -π12 and π12. So for sine, we're just looking at things that are in our first quadrant and in our fourth quadrant. And we're getting into our fourth quadrant by writing that as a negative angle. And so sine here, the only one that gives us back √3/2 is π3, or at 60 degrees. If we were looking at all the values between 0 and 2π, we would also consider what was the value in our second quadrant. But we're not, we're only looking between -π12 and π12. And so in this answer, this is equal to π3. And just look to see, usually you're putting the answer in radians and not degrees, but you could say that this is also 60 degrees. So if I want to look at sine inverse of -1/2, so I noticed that it's a negative value. And so what gives me the negative value has to be in the fourth quadrant. Sine is negative in the fourth quadrant. And first I think about what value of sine would give me back +1/2, which I know is at π6. And putting that down into the fourth quadrant, we would say that this is -π6. So if we said sine inverse of 1, Well, the value of sine that gives us back 1 was pi halves. So if you know your trigonometric functions of those special angles, finding your inverse trig of sine, you just have to determine positive or negative. Is it going to be in the first quadrant or the second quadrant? Not second, fourth quadrant. And then determine your value of what that angle would be. So similarly, we would do the same thing for our cosine function. If you looked at the graph of our cosine function, let's say we had y is equal to cosine of x, and we're graphing cosine. Recall cosine of x, that started at the max value. And so we're starting at 1. At pi halves, we hit the x-axis or midway line. At pi, we hit -1. 3 pi halves. We're back up to the x-axis. And at 2 pi, we're back up to our maximum. So this was one period. And you can see that this just one period of our cosine function, it's not going to pass the horizontal line test. It's not a one-to-one function. And so again, we need to limit this domain so that it is a one-to-one function. And so limiting this domain here for cosine, we want to limit it between 0 and pi. And so notice if we limit it between there, it's now a one-to-one function. So y equals cosine of x. Let's just call this f of x also. The domain is between 0 and pi. The way to write that is 0 is less than or equal to x is less than or equal to pi. So this is going to be the range of f inverse of x, which in this case is cosine inverse of x. And the range of f of x, well, the y values we're hitting are the same as sine. We're hitting all the values between -1 and 1. So the range is between -1 and 1. Or another way to write that is -1 is less than or equal to y is less than or equal to 1. And this is the same as they swap domain and range. So this is the same as the domain of f inverse of x, which is our cosine inverse function. So if we went to go graph this, and you don't really have to worry about having to graph these inverse functions in this class. You just really need to know where we're limiting our domain to make it one-to-one and what the domain and the range of the function and the inverse functions are. But to graph this now, here, let's rewrite it because now our domain and range have changed and we're in between -1 and 1. And our value is between 0 and pi, which is our range. Okay, so here, this one point here, which was at 0, 1, is now 1, 0. This point here, which was at pi halves 0, is now at 0 pi halves. This value here, which was at pi negative 1, is negative 1 pi. And so our function looks similar to this inverse function. So now we can evaluate our trigonometric functions and find the exact value like we were doing for our sine inverse function. Let's look at an example. So if we looked at cosine inverse of root 2 over 2. So we're thinking to ourselves, what value cosine would give me back root 2 over 2? And it has to be between 0 and pi. And so for cosine, it's our bounds, if we're thinking of the unit circle, are in our first and our second quadrant. Cosine's positive in the first, negative in the second quadrant. This is a positive value, so I know my angle's in the first quadrant, and I know cosine of pi fourths is root 2 over 2. So this is going to equal pi fourths. So if I had cosine inverse negative 1/2, I would first think to myself, cosine of what value is positive 1/2? And I would say, okay, 60 degrees, which is pi thirds. And then because this is negative, I need to put this in the second quadrant. And so if you think about it, our reference angle is going to be that 60 degrees or pi thirds. And so to get up to this angle, we can find that angle that got us there by looking at our pi, subtracting off pi thirds. So 3 pi thirds minus 1 pi third is 2 pi thirds. So I know the answer here is 2 pi thirds. One more. So cosine inverse, let's say negative 1. Well, if I thought about the unit circle, cosine is my x value of my point on the unit circle, and my x value is negative 1 for cosine. That's going to be at pi. So when you're dealing with cosine inverse function and you're evaluating, then you need to make sure that you're between 0 and pi. So some of your questions have a composition of two trigonometric functions, a function and an inverse function. So for instance, if you had cosine inverse of cosine of 4 pi fifths. So remember, our cosine function and the cosine inverse function, taking the composition either way, we get back what the argument is. Here we have to be careful. If this value here, when we take it, is not between 0 and pi, because cosine inverse, the value had to be between 0 and pi, then we're going to rewrite it. So, but 4 pi fifths, that's between 0 and pi. So that my answer here is just 4 pi fifths. But look at the following example. So let's say you had cosine inverse of cosine of negative pi fourths. Well, negative pi fourths is not in the range from 0 to pi. And so we have a problem there. So the first thing that you want to do is let's first evaluate the inside function. So we're looking at cosine of negative pi fourths. So I know that's getting me in the fourth quadrant if I was thinking it that way. Cosine of pi fourths is root 2 over 2. And I know cosine of negative pi fourths, fourth quadrant x value is also positive. So that's also root 2 over 2. So we're going to rewrite this as cosine inverse of root 2 over 2. So now thinking about what is the inverse trig function, or what is the value of cosine that would get us back root 2 over 2, which is between 0 and pi. So the value that would get us back there would be our pi fourths. So here's an example where it doesn't just undo each other and give us that argument. And so we have to kind of be careful when we're doing these. Look at one more example. So let's say you had cosine inverse of cosine and negative 5 pi thirds. Okay, so I noticed that, again, negative 5 pi thirds, and I'm dealing with cosine, and cosine inverse is not between 0 and pi. So first thing we want to do is evaluate cosine of negative 5 pi thirds. And so if I draw my angle negative 5 pi thirds, I know that I am going clockwise because my angle is negative. I also know that I'm going to basically add a pi thirds, negative pi thirds there, and that would get me up to negative 6 pi thirds, which is negative 2 pi. So this angle is actually getting me into the first quadrant. And so my reference angle here is going to be pi thirds. And so thinking to myself, again, cosine of pi thirds is what? And cosine of pi thirds is 1/2. So this is cosine inverse of 1/2. And the value between 0 and pi, that gives me cosine of of an angle that gives me 1/2. That is pi thirds. So now let's look at our tangent function. If you look at the graph of tangent, you will also notice that that is not a one-to-one function. Recall tangent of x, so f of x equals tangent of x. And this could be rewritten as sine x over cosine x. We had problems when cosine of x was equal to 0. Those were our asymptotes of our tangent function. So negative pi halves to pi halves. Negative pi halves, we had a vertical asymptote. Pi halves, we had a vertical asymptote. Three pi halves, we had another vertical asymptote. And graphing this, a tangent function looks something like this. And so there is 2 cycles of our period. And you can see that that doesn't pass the horizontal line test. And so we want to limit the domain again. And if we limit the domain, we're going to limit our domain to negative pi halves to pi halves. So notice that at negative pi halves and pi halves, those are vertical asymptotes. So we're not going to include those values. So this is the range of f inverse of x, which in this case is tangent inverse of x, or arc tangent of x. And then our range here, notice our range, we're hitting all the y values. So our range is between negative infinity to infinity, which is the same as our domain of our inverse function of tangent of x. So when we graph the tangent inverse function of x, our domain is negative infinity to infinity, but our range is negative pi halves to pi halves. And these are horizontal asymptotes now here, because we never can touch this value. We would just get really close to it. And so I'm going to denote it by a dotted line. And so plotting our points, so notice here at 0, we have 0. So swapping x and y is 0, 0. Here at pi force, we had 1. And so at 1 pi force. And then at negative 1, or negative pi force, we have negative 1. So at negative 1, we have negative pi force. So our graph looks similar to this. Okay, so just like we had done with the sine inverse function and the cosine inverse function, we need to be careful when we're looking at finding the values of our inverse trigonometric tangent function. So if you were given tangent inverse of root 3 over 3. So you're thinking to yourself, what value of tangent, which is between negative pi halves and pi halves, would give me back root 3 over 3? And so that's at 30 degrees or pi 6. If it asked us to find the tangent inverse of negative 1. So I know that my value is negative, and so I have to be down between negative pi halves and 0. And what would get me there? Well, I know tangent of pi force is positive 1, so it would have to be negative pi force. to get a negative 1. So the other thing that you need to be careful about is, for instance, let's look at this example here. Let's say you had sine of sine inverse of 2. Okay, so sine inverse, the domain is between -1 and 1. And so notice that 2 isn't in our domain of sine inverse. There's no sine value that's going to give us back 2. And so right here, this is undefined. So since that's undefined, the whole thing is undefined. This is not possible. So our next examples are examples where we're trying to solve the equation and find the exact value of each equation. So the first one here, we have 2 sine inverse of x equals pi. So first thing that you want to do in these is you want to isolate your inverse trigonometric function. So you want to get that by itself. So in this case, we don't want the 2 in front of the sine inverse of x, and so we could just divide both sides by 2. And so doing so, we get sine inverse of x is equal to pi halves. So in here, recall when we were talking at the beginning that taking a composition of a function and its inverse function undoes itself. And so we want to get x by itself here. And so we could, because this is sine inverse of x, we could take the sine of both sides. And so we're looking at the sine of sine inverse of x. This is equal to sine of pi halves. So composition of sine and sine inverse gives me back my argument here, which is x. So x is equal to sine of pi halves. And then you need to evaluate what sine of pi halves is, which is just 1. So in this case, x is equal to 1. So if our argument in here was not just the single x, so maybe let's say you had 2 sine inverse of 4x equals pi. So first thing we should do here is probably do a substitution, and we'll come back. And so let's make this a single value. We can do that. We can just say, well, let's choose some variable. So I'm going to choose a. Let's let a equal this 4x. And so here then we have 2 sine inverse of a, which is equal to pi. So let's divide both sides by 2. We get sine inverse of a is equal to pi halves. Again, we can do the same thing that we had done before. So let's undo the sine inverse by taking the sine of both sides. So sine of the function sine inverse of a is equal to sine of pi halves. So sine and sine inverse undoes itself. And so this gives us just a is equal to sine of pi halves, which we know is 1. But we're not done here because we wanted to know what x was. And we had chosen a to be 4x. So let's go back in here and rewrite a as 4x. So we know 4x is equal to 1. And now we can solve for x by dividing both sides by 4. We know x then is 1/4. So let's look at a couple other ones. So let's say you had -4 tangent inverse of x equals pi. So again, we're going to isolate our inverse trigonometric function. So we can do that by dividing both sides by -4. We get tangent inverse of x equals -pi4. We can undo the tangent inverse by taking the tangent of both sides. So we have tangent of tan inverse of x is equal to tangent of -pi4. So tangent of tangent inverse of x is just x, and tangent of -pi4. So I know tangent of pi4 is 1. Tangent, though, for -pi4, it's in our second or fourth quadrant. Fourth quadrant tangent's negative, so this is -1. So looking at one more, let's say we had 5 sine inverse of x minus 2 pi is equal to 2 sine inverse of x minus 3 pi. So I notice in this equation, I have 2 terms that have sine inverse of x, and I have 2 terms that don't have any x in it at all. So we want to isolate the terms that have sine inverse of x to one side and the terms without x to the other side. And so let's just start by subtracting 2 sine inverse of x on both sides. And then let's add 2 pi to both sides. So doing that, we have 5 sine inverse of x minus a 2 sine inverse of x. That's 3 sine inverse of x. This is equal to -3 pi plus 2 pi, which is -pi. And now we want to isolate our sine inverse of x. So we could divide both sides by 3. So we have sine inverse of x equals -pi divided by 3. We can take the sine of both sides of our equation. And so taking the sine of both sides of our equation, sine of sine inverse is going to undo itself, is equal to sine of -pi3. So we have x here is equal to, well, sine of pi3, that is √3/2. I'm in the sine of -pi3, fourth quadrant, that's -√3/2. The other thing you can think about with these, with the negative angles, think if sine is a odd or even function, it's odd. We could have just started here knowing that this is an odd function. We could have pulled out and say this is the same thing as negative sine of pi3. Sine of pi3 is √3/2 with a negative in front. Gives us x is this -√3/2. Okay, so we have an example in front of us. For these examples, we're given our function f of x, we're given the domain of that function, and we want to find the inverse function, and we want to find the range of our original function and the domain and range of our inverse function. So it would kind of be helpful if we thought about the graph of 5 sine x plus 2. And so looking at this, I can tell that my amplitude is 5, which means that my max value would normally be 5, but I have this vertical shift here of 2. So 5 plus 2 is going to be my new max value, which is 7. My minimum value my minimum value of 5 sine x is -5, but I have a vertical shift up 2 units. So -5 plus 2, this gives us back -3. So we have a range of f of x. And this is equal to -3 to 7, including, which that means this is my domain of my inverse function. And if this was my domain of f of x, that means that my range of my inverse function falls between -π12 and π12. So the only thing we haven't done yet is find that inverse function of f of x. And so recall we talked about finding the inverse function. We rewrite f of x as y. So this is y is equal to 5 sine of x plus 2. Once we did that, we swapped our x and our y values. So this would be the same thing as x equals 5 sine y plus 2. We want to isolate our y value now. So let's isolate sine y by itself. So first thing we would do to do that is we would subtract 2 on both sides. And so we would get x minus 2 is equal to 5 sine y. Get rid of the 5 in front of the sine. So let's divide both sides by 5. I'm going to just rewrite the order. So I'm going to put sine y on the left-hand side is equal to x minus 2 divided by 5. And so to undo the sine, we could just take the sine inverse of both sides. And so taking the sine inverse of both sides, we would get sine inverse of sine of y is equal to sine inverse of this x minus 2 all over 5. So sine inverse of sine y, that undoes itself, giving us y is equal to sine inverse of this x minus 2 over 5. Once we got y by itself, that's where we rewrote that function with the inverse notation. So this is f inverse of x. We found to be sine inverse of x minus 2 all over 5. Where the domain of f inverse of x, we said, was going to be between -3 and 7. And the range of f inverse of x is between negative pi halves and pi halves. Let's look at one more of those. Finding the inverse function and finding the domain and range of the inverse function and the range of our original function f of x. So we're given here that f of x is equal to 2 cosine parentheses 3x plus 2 and our parentheses, and we're given that negative 2/3 is less than or equal to x is less than or equal to negative 2/3 plus pi thirds. So they were giving us the domain of f of x. And so that tells me then I know what my range of f inverse of x is. That domain, so negative 2/3, less than or equal to, but it's my y value. Y is less than or equal to negative 2/3 plus pi thirds. I need to think about the graph of this. I know that my 3x plus 2, that is just changing my horizontal stretch or compression. So that's not going to change my amplitude or the max and min. And it's also going to change the horizontal shift. But my phase shift also doesn't change my max or min. And so I can figure out by just looking at this function, f of x equals 2 cosine 3x plus 2, that my max value is 2 and my min value is negative 2. So my range of f of x is between negative 2 and 2. So negative 2 is less than or equal to y is less than or equal to 2. So that means my range, my domain, I mean, of f inverse of x is negative 2, which is less than or equal to x, which is less than or equal to 2. We wanted the range of our original function, and it wants us to find f inverse of x. So rewrite f of x as y equals 2 cosine of 3x plus 2. Swap our x and our y value. So x is equal to 2 cosine of 3y plus 2. We want to take cosine inverse of both sides, but before we can do that, we need to get rid of the 2 in front of the cosine. So divide both sides by 2. We get x over 2 equals cosine of 3y plus 2. Take the cosine inverse of both sides of our equation. We get cosine inverse of x over 2 equals cosine inverse of cosine of our argument 3y plus 2. Well, cosine inverse of cosine undoes itself, giving us just the argument left, which was 3y plus 2. Get y by itself, we would first subtract 2 on both sides. So we have cosine inverse of x over 2 equals, oops, we subtracted 2. So minus 2 equals 3y. Divide both sides by 3, we get y, and y there is our inverse function. So our inverse function, f inverse of x, is equal to cosine inverse of x over 2 minus 2, and then divide that whole thing by